Hello everybody. So today's lecture is going to go a little differently than some of the other ones. Today's lecture is going to be on service feeders and branch circuits, section 8. And we're also going to jump into section 14 and 26 as well. So this lecture is going to be a little different because it's basically going to be just doing one question, or I'm going to show you how to do one question that involves sizing the service feeder for a house, a single dwelling, and we're also going to show a couple branch circuit calculations. And the first part that's going to take most of the lecture, I imagine, is going to be sizing the service conductor size, the overcurrent for the service, and we're going to go through all the calculations for that. So this is a big word problem. Let's just read through it together. There's lots of information. So we have a 2-story house, which has the interior measured dimensions of 8.6 meters by 12.1 meters on every floor. This house has a basement of the same dimensions. So the basement is also 8.6 by 12.1. It is fed from a 120 240 volt 3-wire supply with 75 degrees Celsius termination temperatures for all electrical equipment. So that 120 240 3-wire, if you remember from the last lecture or the last module, that's typically what we feed our house with. And we talked about overhead and underground services. And then in this house we have known loads, which are a 13 kilowatt range, or 13,000 watts, 2,500 watt EV charger without an energy management system. We'll talk about that in a little bit. A 5 kilowatt clothes dryer, 50,000 BTU natural gas barbecue with a 1,500 watt griddle attached. Sweet. Yeah, I want to live in this house now. That's wicked. 1,450 watt dishwasher, 1,550 watt 120 240 volt kiln, 2,100 watt electric tankless water heater, 30 amp 120 240 volt air conditioner, interlocked with a 11,000 watt electric furnace, or 11 kilowatt electric furnace. We'll talk about that interlocking and whether or not that matters or how it applies. So let's jump to the code book and let's start to look at our primary focus, which will be section 8 today. You might notice a highlighter kind of marking the start of section 8. We're going to be jumping around a little bit, so I want to make sure I don't lose my place. So section 8 is circuit loading and demand factors. It's got a couple special definitions, such as the basic load, and that's going to be something we talk about in our house calculation. An important thing for all code calculations, or all the calculations we do in code, is this, it says current calculations, but it's going to talk about what to use when we use voltage to divide. If you remember in your lab classes, sometimes your voltage at the bench, we say it's 120, but you actually measure 117 or 116.9. When we're doing calculations for code, we're going to use what's called nominal system voltages. And as it says, the voltage divisors to be used shall be 120, 208, 240, 277, so on and so forth. So when your house has a 120, 240 volt 3-wire service to it, it's probably not exactly 240 volts, but to get current, we're going to do current is going to break my pencil there. Current is going to equal wattage over volts, or power over source voltage, if you remember from theory class. So watts over volts gives us amps. So when we do this kind of calculation, the codebook's saying, yeah, use nominal voltages. Then we have 8106 talking about use of demand factors. And so this is going to kind of start us down answering that question that I showed in the beginning. So in any case other than a service calculated in accordance with 8200 and 8202, where the design of an installation is based on requirements in excess of those given in this section, the service and feeder capacity shall be increased accordingly. So if we do a calculation and say, oh, this is the service we need, but the requirements, or let's say the customer says, no, my service needs to be much bigger, and here's the paperwork to prove it, then we just meet that requirement. That's kind of what that rule is saying. So we use our demand factors unless we're told otherwise, is another way to look at that. We're going to look at some other sub rules and such in 8106 there in a little bit. 8110 is going to be the first one we jump back to after we look at our main rule for the day, or the rule that question is centered around for the most part, which is single dwellings under calculated load for services and feeders. So, to start off, excuse me, 8200 is going to give us an either or situation. So, the calculated load for the service or feeder supplying a single dwelling shall be based on the greater of item A or B. Now, item A is everything that's below this greater of. And so you might see I have an orange highlight, kind of a unique, hey, look at me, I'm special, highlighted word. So it's going to be greater of item A or B. So either everything it's talked about here, or on the other page, the few things that are talked about in B. It's just these two items. So it's an either or. It's the greater of this or that. Now, I like, for these kind of questions, I like to stay organized. I try to stay organized. It's important to stay organized. Sometimes you can get the right answer the wrong way, which means that you can't repeat the process to get the right answer again because you didn't get it the right way. That just kind of happens in code class. But for the calculations, it's pretty easy to go wrong, to go awry, and get completely wrong answers. So I like to do a methodical item by item of 8200 when I do a service calculation for a house. So first thing we need to do is get the size of the house, and this one is 8.6 meters by 12.1 meters on every floor. It has a basement, and the basement's the same size. Okay, let's start there. And we're going to start there because that's the first item under 8201A. Tells me a basic load of 5,000 watts for the first 90 meters squared of living area, plus an additional 1,000 watts for each 90 meters squared or portion thereof in excess of 90 meters squared. If you want to read item 2 as just 1,000 watts for each 90 meters squared, or portion in excess of 90 meters squared. That one's a bit of a mess to read. And you might notice as we go through this, it says plus, plus, plus. It's basically adding every one of these items up. So if this item applies, or if there's a demand factor that applies, these items get added together. But we need to look at this living area first, which is 8110. And it's just going to tell us the living area designated in 8200 and 8202, but we're looking at 8200, shall be determined from the inside dimensions and include the sum of, so we're going to add together, 100% of the area on the ground floor, 100% of any areas above the ground floor used for living purposes, and 75% of the area below the ground floor. Below the ground floor would be the basement, for example. So that's how we find our living area. And the question gave us interior measurements. That's good. If those are exterior measurements, we may have to subtract the thickness of the wall, but that's giving us interior measured dimensions. So that's how we're going to find out our living area. So the living area is calculated as such. Now, real quick, just a reminder, the area of a rectangle, so we're trying to figure out, if this is a top-down view of our house, we're trying to figure out all of this area, which is width times length. And so if we think of our house just as a rectangle, as a box, and we need to figure out the area, but we're just given dimensions, we could say, let's put 8.6 here and the 12.1 here, and we just times those together to get our area. So main floor equals, and we'll just grab our calculator, 8.6, show that on the camera, times 12.1. It's going to give me 104.06 meters squared, because I just times meters by meters. I know that the second floor is going to be the exact same size, and 8110 tells me to take that at 100%, so I'll just write the same number for that. And then it tells me to take, the question tells me the basement is the same size, so I don't need to account for any frost walls or any extra temperature or other requirements that you might put in a basement. So the basement is the same size, but 8110 tells me to take 75%. So my basement is going to be equal to 104.06 times 0.75. 0.75 is 75%. So then my basement is going to, or what counts for in the basement towards my calculation, is 78.05 meters squared. I just rounded up that 4 to a 5. So I'm going to add those together. And so my total living area is going to be plus 104.06 plus the basement, which was 78.05, 286.17 meters squared. Now that living area that we just figured out is what we're gonna, or what's gonna count towards what we call our basic load. And the basic load, or how I get the basic load after getting the area of the house, is going to start to look like this. So 8200 1A, item I, or 1, a basic load of 5,000 watts for the first 90 meters squared of living area. Perfect. So this is how I make sure that I personally count the right amount of watts for the basic load. So the first 90 meters squared. What I do, and you can do it differently if you find a better way, but what I do is I minus 90 meters squared, and that's my first 90 meters squared that I'm accounting for. And each time I subtract 90 meters squared, or I'm able to, I put the wattage associated with that based on item I and item II, or 2 I should say. And so the first one is 5,000 watts. And so 286, see if I still have that number, there we go, minus 90 equals 196.17. Perfect. Item 2 is saying an additional 1,000 watts for each 90 meters squared, or portion thereof in excess of 90 meters squared. In excess. So, I have an additional 90 meters squared that I could subtract, which gives me 1,000 watts. And that's going to give me 106.17 meters squared left. And so I'm going to bring that down here and make sure I show my work and show it on the camera, I guess. I can still subtract another 90 meters squared, which is just 1,000 watts again. And that's going to give me 16.17, which means I still have some left over. And basically you're going to keep going until you hit a negative, and then you're going to stop. You're not going to add any more wattage. But I still can subtract another 90 meters squared, which would be another 1,000 watts. And that's going to give me a negative whatever number. So now I stop, right? Little stop sign. Stop. Do not proceed. Do not pass go. All that stuff. And stop. So now I have my wattages, and each of these numbers just adds up towards my basic demand. So 5 plus 3,000 is going to give me 8,000 watts. And now for the overall calculation, I'm going to start to organize to make sure I don't miss anything. I'm going to organize it like this. So I'm doing rule 8200, 1, A, I. And it's actually also II, or 2. So that's because I know what this subrule and item is talking about. I know that's my basic demand. And that's the first thing I'm going to figure out for this service calculation for a house to add up. So, number 3, or item 3. Let's see what that's all about. So, item 3 is talking about any electric space heating loads provided for with demand factors as permitted in section 62. Okay. And I've kind of cheated here by, I already found the rule for myself a long time ago. But the electric space heating loads are going to have a demand factor that we're going to get out of section 62. Cool. Plus, any air conditioning loads with a demand factor of 100% subject to 81063. Okay, so let's go back to our question here. What does it give us? What's in this house? At the bottom, we have an air conditioner with a rating, with a value, and we have this electric furnace with a value, and they are interlocked. The air conditioner is interlocked with an electric furnace. And so what that means, if you look at some thermostats have this, and if yours does, you can look at a thermostat that you can switch between. It has like a mode button, and you can switch between heating and cooling, and sometimes a fan function as well. Pardon me. And so what that means by switching the modes is that the thermostat will not run cooling at the same time as it will run heating. And so because of that, we could say in that kind of application that the air conditioner is interlocked with the furnace. And so let's look at what that means towards our calculation, because it talks about 81063. So on the other side of the page here, it's talking about use of demand factors. And specifically, we're taken to subrule 3. which tells us where interlocks are installed to prevent simultaneous operation, which is what I was just talking about with the thermostat that has the mode option, of electric space heating and air conditioning loads, whichever is the greater load, or the larger value, would be another way to read greater load, shall be used in calculating the demand. Okay, so we're not going to use both. We're not going to add in air conditioning and heating in this situation because they're interlocked. And so we're not really sure which one's greater, though, because we don't have a wattage for the air conditioner, for one. And I don't know what section 62 is going to tell me to do with this 11,000 watts of the electric furnace. So I'm going to draw myself a little divider here on my page. I'm going to remind myself that this is I. And I'm going to take 30 amps. I'm going to figure out my wattage of the air conditioner first, because that one's a bit more straightforward. Once I have my wattage, I know the demand factor is 100%. And so 30 amps times 240 volts equals, that's just my power formula, I times E. 30 times 240 gives me 7,200 watts. You might see this in the field, or it shouldn't be on any questions exactly in first period, but you might also see watts as VA. And that's the same thing as far as we are considered in first period. You get more into the differences between them in later years, but I mean, just practically thinking, if P equals I times E, well, sure, watts is volt amps, right? Volts times amps gives you watts. So watts VA, pretty straightforward thing to think of. So I just want to point that out in case that comes up in a question or TQ or what have you. So that's my AC, and I'm going to give myself a little bracket to say that's my air conditioner. All right, now for my heat, I need to go to section 62 to figure out what I can do with my 11,000 watts. So section 62 is for fixed electric heating systems, and unless you're Hercules or the strongest, winner of the strongest man in the world competition, a furnace is a fixed electric heating system, right? So that's where we're going to find some information for our furnace and how to count it towards our main feeder service for the house. And so when we flip the page and we see that 62118, it's called demand factors for service and feeder insulated conductors. Well, that seems pretty perfect. And when we look down at subrule 3, it's telling me that notwithstanding subrule 1, so forget whatever was said in subrule 1. Perfect, I didn't even read it yet, so I don't have to know what I forgot. Where heating installation in a building for residential occupancy, that's what we're dealing with, is provided with automatic thermostatic control devices, which would be a thermostat, in each room or heated area, so everywhere where the heat provides heat. The ampacity of service or feeder insulated conductors supplying heating devices only shall be based on the following. So we have this line plus the second line. First, 10,000 watts of connected heating load at 100% demand factor, plus the balance of the connected heating load at 75% demand factor. So this is saying you take 10,000 watts plus 75% of anything that's more than 10,000 watts. So if you had 20,000 watts, you would take 10,000 watts plus 75% of the other 10,000 watts. Cool. So maybe that's what we do for our furnace. But subrule 4, if we keep reading, tells me where a service or feeder insulated conductors are used to supply an electric thermal storage heating system, duct heater, or an electric furnace, the connected heating load shall be calculated at 100% demand factor. Oh, okay, perfect. So my demand factor for my furnace is 100%. So that's pretty straightforward. You'll note that I told myself here, must be told. So if it just said it was a furnace, I don't assume that it's an electric furnace. But because in this question, it told me it was 11,000 watt electric furnace, I know to take it at 100%. And since they're interlocked, or since the furnace is interlocked with the air conditioner, I know I'll just take the greater of the two. So in this case, I'll be taking my heat load because it's larger than the air conditioning load. And because they're interlocked, I mean, if we just think about this logically for a second, they're interlocked, so only one's going to run at a time, right? So if we size the entire house calculation towards the larger load, that's going to make up for the other load, if that makes sense. Hopefully that makes sense. So 11,000 watts gets added under item 3. There we go. We're cooking now. We're moving along. So item 4, I'm just moving down. I'm just reading each one to figure out what gets added in. Item 4 is going to give us any electric range load provided for as follows: 6,000 watts for a single range, plus 40% of any amount by which the rating of the range exceeds 12,000 watts. Okay, so once again, the electric range, 6,000 watts, plus 40% of any amount by which the rating of the range exceeds 12,000 watts. Now, what that means, let's just add our next item here, item 4, and then we'll say item 4. The range in this question is, I believe it was at the top, here it is, 13,000 watt electric range. Okay, so item 4 tells me 6,000 watts plus 40% of any amount by which the rating of the range exceeds 12,000 watts. So it's going to be 6,000 plus, it's a 13,000 watt range, so that means I only have 1,000 watts above 12,000 watts, if you want to think of it that way. So plus 1,000 watts times 0.4, which would be 40%. And that's going to give me, put that into my calculator here, plus 1,000 times 0.4, make sure you get the right amount of zeros, is 6,400 watts. So that's how we calculate for that one range, 6,400. Moving on, let's see what item 5 is about. Item 5 is telling me any electric tankless water heaters or electric water heaters for steamers, swimming pools, hot tubs, or spas with a demand factor of 100%. Well, that's pretty straightforward. So I have an electric heater for my hot tub. Count that as 100%. Electric tankless water heaters, also at 100%. Okay, cool. Let's check out my question. Let's see all the loads we have. So we had the range, we got an EV charger, clothes dryer. And if you get a question like this on paper, or if you write down all the loads that are in this question on a scrap piece of paper, it might help you just to check them off as you put them through your calculation. I just work through the rule, and that kind of keeps me organized. I just grab the loads as I need them. Electric tankless water heater. Oh, perfect. So it's 2100 watts. It's an electric tankless water heater. Let me just make sure. Yeah, that's exactly what it's talking about. Okay, so no calculation needed for there. It's just 2100. Perfect. Demand factor is 100%. I don't have to reduce that or change that or times anything by percentages. Great. Okay, that's a pretty simple one. So next up would be item 6, and it's giving us another rule here. So except as permitted by 8106.11. All right, so when it says something like, it's not really good English sometimes in the code book, because it's starting out with the exception. That doesn't make sense. That's not how I read. So if you want to, and this is what I do, when it says except as blah, 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 I just ignore that and I go to the spot after the comma. I read the spot after the comma first, and then I go back to the except. Because starting with except is nonsensical to me. So I read item 6, any electric supply equipment loads with a demand factor of 100%. Perfect. That EV charger at 100%, except 8106.11. Okay, so it's 100% unless it's this. Let me go check that out. So 8106.11. For the purpose of rules, yep, that was me. 8201 AVI and a bunch of other ones, where an electric vehicle energy management system, as described in subrule 10, monitors the consumer service and feeders and controls the electric vehicle supply equipment loads in accordance with Rule 8500. The demand load for the electric vehicle supply equipment shall not be required to be considered in the determination of the calculated load. So, if there's an electric vehicle energy management system, we're not going to count that EV charger towards the service. And just briefly how those energy management systems work, and it kind of explains it in subrule 10 as well, but in order to not overload the service, for example, if someone comes home from work, plugs in their EV, or their electric vehicle, I should say, goes into the house and starts cooking right away, that's 2 very large loads that the service has to deal with. And so how an energy management system works is it monitors the main service for the energy usage. And so when you come home and plug in your car, the energy management system might not start charging that car right away. It might wait for a lower demand time, such as overnight when everyone's sleeping and the lights are off and no one's cooking, to allow that EV charger to charge the car. And so because of how that management system works, if there is one, you don't have to count the EV charger towards the service, because it's not going to be running when other loads are running in the house. So let's go check out our question. Here we have a 2500 watt EV charger without an energy management system. Well, shit, all that reading, all that possibly newfound knowledge for nothing. It's just taken at 100%. So, but we have to read it to see if maybe it wasn't going to be counted, or to see if there was some other demand factor to be applied. But there's no energy management system, so we add that in at 100%. Then our last item for this calculation, VII, or 7. Yep, probably 7 for my Roman numeral reading. We've had all these specific loads and calculations and demand factors, and then item 7 is going to say any loads provided for that have a rating in excess of 1500 watts. So 1500 watts is not in excess of 1500 watts. Might sound like I'm repeating myself, but 1501 watts would be in excess of it. In addition, added to those outlined in items I to VI. So all this stuff we've done so far, plus everything in excess of 1500 watts at 25% of the rating of each load. If an electric range has been provided for, which we have, or 100% of the combined load up to 6,000 watts plus 25% of the combined load that exceeds 6,000 if an electric range has not been provided for. So, if you'll notice up here at item 4, basically B here is saying if you're not going to calculate a range into the service, calculate a range into the service. This is basically what B is making us do. But we have a range, so we're just taking 25% of each load in excess of 1500 watts. So, if we haven't already touched on it, we take it at 25% if it's in excess of 1500 watts. So, I go like this, VII, and I start looking through what I have not accounted for yet. So, range, yep. EV charger, yep. Clothes dryer, oh, nope. And that is definitely in excess of 1500. So I go 5,000 watts. And that's I might even go like this to make sure I know what I've accounted for. That's my dryer. Plus 50,000 BTU natural gas barbecue with a 1500 watt griddle attached. What a beauty. Man, I want to spend my summers here. But 50,000 BTU, I do not give a crap about because that's natural gas. That's not electricity. Get out of here. 1500 watt griddle, that's not in excess of 1500 watts. I don't care about that. So, I don't count that. 1450 watt dishwasher, nope, that's definitely less than 1500. Ooh, but this guy, 1550 watt, 12240 volt kiln, sweet. I'm gonna be drying some pottery. I'm gonna dry out some firewood with my kiln. I don't know who has that in their house, but this one has it. It's in excess of 1500 watts, so we're going to have to count it. And then I don't think anything else goes towards it. We already counted that tankless water heater, air conditioner, electric furnace, perfect. So plus 1550 watt kiln. Maybe they have an art studio. They're making lots of pottery. And so I take those two values, that's going to add up to 6,550 watts. And I just times it by 0.25 for 25%. So 5,000 plus 1550 times 0.25 gives me 1,637.5 watts. Towards my service. So I'm going to add all of those up. That's all of the items for A. And so I left my other loads. Sometimes we just call that the other loads, that item VI. And I'm just going to work my way up, making sure that I include the proper amount of zeros, otherwise it's going to throw your calculation out of whack. And that's also why I write down every value. So in case my calculation comes out wonky or weird or whatever, I can go back and just add it all up again. So 1,637.5 plus 2,500 plus 2,100 plus 6,400 plus 11,000 plus 8,000 gives me 31,637.5 watts. Awesome. Not sure why I wrote watts, but just wanted to make sure. I love saying watts. I love writing watts. Lots of watts. So that's my wattage for item A. But 8200 said, yeah, that's cool you did all that work, but you go ahead and check B because you got to take the greater of A or B. So as a dutiful servant of the great codebook, I'm going to go check out B because I know I got 31,000. And B is going to give, if I can show it on the camera, 24,000 watts, where the floor area, exclusive of the basement, is 80 meters squared or more, or 14,400 watts, where the floor area, exclusive of the basement, is less than 80 meters squared. But we already know from calculating at the top, and this is why I did each floor individually, we already know that one floor is above 80 meters squared. So we're definitely going to look at 24,000 watts, but that is less than everything we just did for our calculation. So I don't care about item B. I'm going with item A because that's the greater value. And so now I need to size my wire and my overcurrent. We're going to talk about sizing overcurrents here. But first, I'm going to divide this wattage by 240 volts because it told me that's what my service was. And those watts are going to be across both phases or both lines, both hot wires, both live wires, both ungrounded wires. That's all the words I can think of for those wires. So I use my 240 volt divisor. That's my nominal system voltage. It's a 120, 240 volt system. So 31,000. That's not my calculator. Nope, it's gone. Okay, 31,637.5 divided by 240 gives me 131.82 amps. So if you remember from our section 4 stuff, I don't believe it's in the question, but let's just say that we have 3 RW90 wires that are run in PVC underground. That should have been included in the question, but we're just going to say for our practices today, it's 3 conductors in PVC underground. Goes up to the meter, from the meter to the panel, etc. And so that ampacity is going to go on the conductors. And so we're going to go to table 2. Should be able to find it. It's pretty good worked in codebook. And we're going to remember that the question gave us 75 degrees Celsius termination temperatures. And so we're going to look down the 75 degree column and maybe use a pencil to keep ourselves lined up with the right conductor size. And 1 gauge, nope, too small. And we're going to go to a 1/0, good for 150 amps. So I'm just giving myself, yep, this is what I did. I went to table 2, which gave me a 1/0, good for 150 amps. Cool. And now I'm going to size my overcurrent. And when we size overcurrents in general, and I'm saying general because we're working off a general section of the code book. If you remember that, if you don't, you can go look back at the preface to see or the preface, to see what's general sections of the code book and what are the supplementary or specific, or I say boss sections. but we're in a general section. So in general, we size our overcurrents to protect the wire. The wire is sized to deliver current to the load, but if that wire breaks, it's all for nothing. So we size our overcurrent to protect the wire. And in code class, we're going to do maximum overcurrent and a minimum wire size. So sizing the overcurrent to protect the wire is going to take me to table 13. And I know it's table 13 because, well, I've done this a few times, but also if we go to section 14, which may be a new section for us. Section 14 is protection and control, and the overcurrent protects the wire. And under section 14, we have 14.104. There's other stuff too, but we're just going to look at, for our purposes today, we're going to look at 14.104, rating of overcurrent devices. And subrule 1 tells me that the rating or setting of overcurrent devices shall not exceed the allowable ampacity of the conductors that they protect. So we size our overcurrent to protect the wire, and it can't exceed the allowable ampacity of the conductors. Except, see, that's how you use except properly. But I'll get off my soapbox here. Except where a fuse or circuit breaker having a rating or setting of the same value as the ampacity of the conductor is not available, and the maximum calculated known load is in accordance with the rules of section 8, the ratings or settings given in table 13 shall be permitted to be used within the maximum value of 800 amps. So let's jump to table 13 and see what that means. Just to go back here for a second, B is talking about equipment, wire, and flexible cord. We don't care that much. We're not dealing with that. And then C is as provided for by other rules of this code. So that's talking about the specific sections. Other specific sections of the code may say something different about overcurrent devices, but we're in a general section, so we're going to deal with general rules. And then we're going to talk about subrule 2 in a little bit. But for now, let's go find table 13, which is somewhere in the table section. I'll find it. So, table 13 has these two categories, or these two columns, I should say. We have the ampacity of our conductor, and we have the rating or setting permitted on our overcurrent. And it even says at the top here, rating or setting of overcurrent devices protecting conductors. And that star is just saying for general use or not otherwise specifically provided for. Now, as you saw and as you've seen me been doing, my 1-aught I wrote good for 150 amps. And then I'm going to take that 150 amps, and I'm going to go to table 13. And the reason I write down that 150 is because that's what I'm going to use this column. I'm going to take that 150 and go down this column, and then it stops at 110, so I'm actually going to go over here, and there we go. 126 to 150 ampacity of conductor gives me 150 amp overcurrent. Probably using a breaker here for this service feeder to a house. And so table 13 gives me a 150 amp over current, just OC, that's over current, sure. That's how I like to write it. However you want to do it to say that it is what it is as long as you're clarifying that it's the overcurrent, that's fine. So there we go. There's our first house calculation. And there's our answers to this first one. We showed our calculations, we get our conductor size and overcurrent size. Now, this question is also giving us basically the second half of the module, which is branch circuit calculations. And it's asking me for the branch circuit conductor size and overcurrent size for range, dryer, air conditioner, which is a continuous load in this house. So continuous load, that probably matters. And the kiln, that mysterious little drying device. So I'm going to start with the kiln because that seems like the smallest. It's 1550 watts, 120, 240 volt. Okay, cool. So I'm going to divide myself here. My kiln is 1550 watts. I'm going to divide by 240 and divide by that nominal system voltage. And that's going to give me some kind of something. 6.4, let's say 6.46 amps. It's not going to matter that much because the tables don't really use decimal points for amperage. 6.46 amps. I need to know my conductor size and my overcurrent size. So I'm probably going to run, it's in a house, so I'm most likely going to run some kind of cable through the house. I'm not going to be running it in conduit or anything crazy. It's 120, 240. So that means I'm probably going to run a 3-wire, and that's 3 wires in a cable. Cool. So I don't think I have to go to table 5 at all. Actually, I know I don't, because I did that section 4 module. And so I'm going to take that to table 2. I can't size my overcurrent yet because I don't know what wire size I'm using. So remember that the codebook says our default is copper. So I know that I'm going to use copper. I know that the question said all termination temperatures are 75 degrees Celsius. So I'm in the 75 degree column, and whoop, that didn't take long. The smallest wire, because it didn't say flexible cable or anything else, the smallest wire I can use here would be a 14 gauge. So perfect. And that's good for 20 amps at 75 degrees Celsius. Perfect. So table 2 gave me a number 14. Good for 20 amps. Sweet. I'm going to take that over to table 13. I'm going to flip forever. And table 13 is giving me 20 amps is a 20 amp overcurrent. Perfect. Equals 20 amp overcurrent. So that 20 amp overcurrent is going to protect my number 14, probably. Spoiler alert, no. Thou shalt not do that. That is not allowed. No, 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 no. Because if we go back to where we got that wire from, you may have already spoiled it for yourself because I wrote 14104 right here. And 14104, the reason I know that it's 14104 is these little squiggly S with a circle in the middle things beside 14 gauge, 12 gauge, and 10 gauge. Whenever you see something like that, like an asterisk or these little crosses beside things in a table, it's directing you to look at notes associated with the table. And so our little S squiggle thing, I have no idea what that actually is going to send us over to C rule 14104 2. Okay, well, we looked at 1. Why is 2 so special? And if you've ever wired up houses, you probably already know, or you might have already known that a 14 gauge does not go under a 20 amp overcurrent. And the reason that is because it's code. So 14104, subrule 2, except as provided for by subrule 1c. So once again, you don't start a sentence by saying except. So the rating of overcurrent protection shall not exceed this stuff except 1c, which is just telling us other parts of the code book, which we're not in, so we don't care about this except. The rating of overcurrent protection shall not exceed 15 amps for number 14 copper. We got a number 14 copper, so I guess we already know what overcurrent to use. 20 amps for 12 gauge copper, 30 for 12 gauge copper, 15 for 12 gauge aluminum, and a 25 amp for 10 gauge aluminum. So that means that it's not a 20 amp. I'm not even going to use table 13. I don't have to. I'm going to go to 14104.2. That's a 15 amp overcurrent. But I'm still good because a 15 amp overcurrent will supply enough power or enough energy or electrical amperage or whatever. That 15 amp overcurrent is still going to suffice for the 6.46 amp kiln. So I'm good. I'm covered. That one's sized. And we learned about 14104.2. So bonus. Another load it asks us about is, or requires that we size the branch circuit, is the range, which was 13,000 watts. Your range in your house is 120, 240. It's a 3-wire cable that goes to that. So we're going to divide that by 240 volts, which is going to give us 13. 54.16 amps, but hang on, that's not actually how we do ranges. Getting ahead of myself. Let's jump back to section 8. And we're going to go to branch circuits. Maybe should have looked at first for the kiln, but let's see if anything is gonna affect us here. So we have branch circuits for supplying ranges, or branch circuits supplying ranges, that is. We got data processing equipment, so those are probably special enough to get their own sub-rules. We have maximum number of outlets per circuit. So an outlet could be a light socket, it could be a receptacle. It's just an outlet ready to be used. And then that's it. So our kiln is probably sized appropriately. But let's see what it says about our branch circuit supplying electric ranges. So conductors of a branch circuit supplying a range in a dwelling unit shall be considered as having a demand of 8,000 watts, where the rating of the range does not exceed 12,000 watts, or 8,000 watts plus 40% of the amount by which the rating of the range exceeds 12,000 watts. So quite a bit similar to how we sized it for the service feeder. It talks about for ranges of cooking units installed in commercial, industrial, and institutional establishments. That's not what we're talking about, so that doesn't matter. And the demand loads given in this rule shall not apply to cord-connected hot plates, rangettes, or other appliances. Cool. Don't care because we got a range. So 8,000 watts plus 40% of the amount that exceeds 12,000 watts. Okay. So it's not just straight up divided by 240. It's a range. So it has a special calculation for it. Also going to get rid of this 8,000 because that's, or sorry, this 13,000 because we're going to use 8,000. And so 8,000 watts, sorry, 8,000, not 800, times the portion that exceeds 12,000 watts at 40%, once again is just 1,000 watts, times 0.4, is going to equal 8,400 watts. And that's the number that I'm going to use. I'm going to divide by 240 still, which is going to give me 35 amps. I already know, because I remember 14104.2, that a number 10 is not going to be good for this, because a number 10 can only go under a 30 amp breaker. So I know that it's going to have to be one size larger at least. But let's go to table 2. Let's make sure that's actually going to cover our range demand. And so a 10 gauge ain't going to cut it. It can only go under a 30 amp. Don't care what this says. But a number 8 will, because it's good for 50 amps. So that's going to give me a number 8, good for 50 amps. Now I'm going to take that to table 13, which is going to equal, and sometimes I'll have a variety of highlighters doing one of these big calculations just to mark all the tables and stuff that we're going to need. Save yourself the time from flipping. Table 13, 50 amp wire, 50 amp overcurrent, perfect, covered. Sorry, should show the camera there. So there's my overcurrent and there's my wire for the range. Now, this is diagram 1 of your codebook, page 530. And this has some general receptacle layouts. And I flip here so we can look at the dryer and the range receptacles. Now, I'll let you guys follow the module and where it directs you, but it's going to send you to section 26, which is going to talk about all kinds of electrical equipment. But I'm going to specifically, let's just smack the camera with the codebook, that's good. I want to specifically look at 26744, because 26700, sorry about that, is talking, or sorry, receptacles, and 26700 and on. And then we're going to flip over to 26744, which is under that, the subheading of electric heating and cooking appliances. And so receptacles are going to be on breakers that are not going to harm the receptacles, essentially, is what this area is talking about. And so 26744 is talking specifically about electric heating and cooking appliances. And so it's going to talk about where an electric clothes dryer having an input in excess of 1500 watts at 115 volts, but not exceeding 30 amps, is intended to be installed in a dwelling unit. A receptacle 1430R, as shown in diagram 1, which we just looked at, shall be installed for the supply of energy to the appliance. So if you're going to put a dryer in, it has to be a 1430R receptacle. And then it talks about in excess but not exceeding 30 amps, shall be cord connected, an attachment plug, 1430p. Okay, cool. Where a freestanding range, electric range, having a calculated demand of 50 amps or less, so that's the range we have for this house, is intended to be installed in a dwelling unit, a 1450R, shown in diagram 1, shall be installed for the supply of that electric range to the appliance. Now, a 1450R is good for 50 amps, and we have a 50 amp overcurrent, so we're good. But the code rule is also going to give us this one minimum overcurrent exception, which is that the receptacle required by subrule 4, this 1450R, shall be permitted to be connected to a branch circuit rated at not less than 40 amps. So if you were to put in a 40 amp breaker for the range in a house, that's why. That's why we can go for a smaller overcurrent than what the receptacle is rated for, is because of this rule right here. But in code class, and I believe the module backs me up on this as well, or the module states it. I got to back up the module because ultimately the module's right. In our code class, we're going to go maximum overcurrent. So the range is going to be a 50 amp overcurrent because that's as big as we can do it. Now the dryer is going to be a bit simpler. It doesn't have any specific branch circuit rules, so we just take, branch circuit calculation rules. We just take that 5,000 watts. We're going to divide by 240 because your dryer gets a 200 and is 240 volt in pretty much every dryer I've seen. So that's going to give us, divide by 240, 20.83 amps. I'm not even going to look at table 2 or table 13. I'm just going to remember 14104, subrule 2. And you don't have to memorize that. I just have from use. So that's going to give me a number 10, which I still know is good for 35 amps. I'm still going to put that there. But I also know that it's going to be a 30 amp overcurrent because that's above 20. So number 12 isn't going to cut it. And the dryer receptacle is a 1430R. So it's going to have a 30 amp overcurrent regardless because the overcurrent is going to match the receptacle. And I know that a number 10 cannot go on anything bigger than a 30 amp. So I know that it's going to be a number 10 as well because of 14104. And because I know a number 10 can handle that load as well. The wire still has to be able to handle the load regardless of all the other things going on. So the last thing we're going to look at is that continuous load air conditioner thing. If the question doesn't tell you that a load is continuous, then we assume it's non-continuous. And what that means for our application is that we have a 30 amp air conditioner. And when a load is running continuously, it's going to cause excessive heat on the wire, right? When we run current on a conductor, it starts to create heat. If we have too much current or the current's on there for too long, it's going to create even more heat. So what we do for sizing branch circuits, what we do for the calculation that is we take that load and we divide it by 0.8. And we'll just call this as our continuous load. And that's going to give us a larger value. And we're going to use that larger value to compensate for the fact that it's a continuous load. So 30 amps divided by 0.8 is going to give me 37.5 amps. So I'm now going to take that value, that's my new value, that I'm going to size my wire based off of. So let's jump to table 2. .75-degree column, and we'll say for this purpose that the air conditioner is fed by a 3-wire cable. There's nothing funny going on in that regard. And we're gonna find 37.5. Nope, it needs to be a number 8. And I remember 14104, so I know that number 10 wouldn't work anyways. But I'm repeating myself now. A number 8, good for 50 amps. 50 amps. And I know from the range question that there is a 50 amp overcurrent, so I'm going to say table 13 equals 50 amp overcurrent. And so in section 8, it tells you how you know or how to account or calculate for whether or not a load is continuous. For our purposes, if the question doesn't say, for our purposes in code class, If the question doesn't say that it's continuous, we assume that it's not, and so we don't worry about this 0.8 to accommodate for that continuous load. And that should be it for today, and have a good time.